Welcome along to this last video on the normal distribution for the S1 syllabus for CIE Maths. In this video we're going to be looking at the normal approximation to the binomial. This is one that a lot of students find pretty tricky to get their head around, but it's always in the exam. It's always worth a question worth about 5 marks, so it's important to try and nail this. What we're going to be doing here is starting with a situation that is a binomial distribution. So I've just got the 4 conditions there for the binomial distribution, and we were talking about them in the last problem as well. So there's 4 conditions there that you should be familiar with for the binomial. And we're going to see what happens as we increase the value of n, the number of trials in a binomial, and see that we can actually use the normal distribution to solve this certain kind of binomial distribution problem. So here I've got a picture of a binomial distribution for n equals 3 and p equals 0.5. So we've got 3 trials. The probability of a success at each trial is 0.5, and this little bar graph shows the probabilities of what you're going to get if you ask the question, what's the probability x equals 1? You're going to get about 0.37 there, 0.38, 0.375 in fact, exactly. It's the equivalent of asking the question, I have 3 coins, they're fair coins, and what's the probability of getting 1 head if I toss 3 coins, or 2 heads, or 3 heads, or no heads? Okay? So we can look at what happens as we change the number of trials here and see what happens to the shape of the binomial distribution. Okay, so imagine that's 6 coins now, and I want to know the probability of getting 3 heads exactly. You can see it's just over 0.3. Let's ramp this up a bit more. So now I've got 10 heads with a probability of 0.5. You can probably start to see what's happening to the shape of this distribution. And it's no surprise, given the title of this video, what actually happens to it. Alright, I can keep going further and further and further along here, increasing the number of trials, and you can see that the shape very much approximates a normal distribution, a bell-shaped curve. Let's make the number of trials 20 now, and let's change the probability of success from 0.5 to, let's say, 0.1. You can see now that the shape of the distribution has changed, and it's much more skewed towards the lower values. And that will become even more apparent if I make the probability much smaller, 0.05, or something smaller like that. You can see now the normal distribution is not a good approximation. The shape is not symmetrical at all, doesn't look anything like a normal distribution. So it's not just the number of trials that's important here. If I increase that to 40, let's say, number of trials to 40, you can still see, even with a small probability, it doesn't work. If I make that probability 0.9, still, normal distribution, no good, is it? If you have a look at that, it's a little bit skewed there. I'll make that 0.95. Same thing, normal distribution, not such a great approximation. So there's kind of a balancing act here, that the value of p has to be fairly towards the middle, I say. So if I make that 0.6, now we're looking good. Value of n equals 40 and p equals 0.6. The normal distribution looks like a pretty good approximation there. These little diagrams show what we've just seen in Excel, what happens as we increase the value of n. And I've got p equals 0.5 in each of these ones here as well. The cutoff that we say is we want NP, or the mean here of the binomial distribution, to be greater than 5, and n times 1 minus p also greater than 5. As I just showed, if you make p really big, 0.95 or 0.99, that it's also going to mess with the shape and hence the appropriateness of this approximation. So you need both of these conditions to be satisfied. So here's the summary of what happens here. We start with a binomial distribution. As long as n times p is greater than 5 and n times 1 minus p is greater than 5, we can say that the distribution is approximately normal. And what are the parameters? The parameters of our normal distribution are, well, the mean is going to be just the mean of our binomial distribution, n times p, and the variance is just the variance of the binomial distribution, n times p times 1 minus p. These are on your formula sheet, the mean and variance for a binomial. They're the parameters that we use for our normal approximation. One more important point to make here. when we're calculating these probabilities going from the binomial to the normal distribution. Because we're approximating a discrete distribution with a continuous one, we have to do a continuity correction. So let's visualize this. If we consider finding the probability of x being greater than or equal to 31 for a binomial distribution. So if we're going to include 31, what we need to do is actually work out the area under the curve from 30.5 and up. Now that area under the curve matches, if you like, the area of each one of these bars as we move up. Okay, so basically for doing a continuity correction, you just need to go up or down 0.5 from the value you're asked, depending on the wording of the question. So if the wording of the question was more than 31, that means that we'd be wanting to find 32 and above, so we'd go to 31.5. If we were asked to find the probability that x was less than 31, that implies that we're not including 31, so it would be 30 and below, so we'd go to 30.5. At least 31 implies that we're including 31, so we'd go to 30.5, and at most 31. So 31 and down, that wording implies that we're including 31, so we want to go to 31.5. So you've just got to go up and down 0.5 depending on the wording, and you'll get used to it after you see a few of these. So here's an example of the process that you need to go through. I use this example with the astronauts back with the binomial distribution. So in this case we've got 40 astronauts. The probability is 0.2 of each getting space sick. And I want to know what's the probability that at least 10 will get space sick out of that 40. So I've stepped this out very carefully. Step 1, we need to define the random variable in distribution. So x is the number of astronauts who get space sick. This is binomial. Okay, it satisfies those 4 conditions. Either an astronaut gets space sick or he doesn't. Space sickness is independent. The probability is always the same, 0.2, and there's a fixed number of trials, 40 astronauts. So the underlying distribution here is binomial. Step 2, check that the approximation is appropriate. So we want n times p, 40 times 0.2 is 8, yep, that's good, greater than 5. And we want n times 1 minus p to be greater than 5. Yep, 32, no problems. So we can use the normal approximation. You need to write that down. Find the mean and standard deviation. So using our formulas from the tables for our binomial distribution, the mean is n times p. The variance n times p times 1 minus p, 6.4. So x is approximately normal. See, I've got these 2 squiggly lines, meaning approximately normal with a mean of 8 and a variance of 6.4. Now we're going to solve the problem. The continuity correction here, at least 10 astronauts. That implies that we include 10. So we're looking at 10 and above, so to include 10, with our continuity correction we need to go down to 9.5. The rest of the question is just straightforward normal distribution. The probability x is greater than or equal to 9.5 is, probability of z is greater than or equal to x minus the mean over the standard deviation. Use the exact value here. As I've got, don't use the rounded value, the square root of 6.4, and put that in. You're going to get the wrong z value. So use the exact value, the square root of 6.4 in your calculator. That gives us this z value. Because we're going there and above, if you've got one of the Casio FX 991 ESs, we'd be using R in that special menu I was telling you about before. So you just put in R of this number here and it would give you the answer. If you're looking at the table, you'd look up 0.593 and you'd say 1 minus whatever that tells you. So the final answer 0.2766 or 0.277 to 3 significant figures. One more example I'll just go through quickly. We've got a driver testing centre showing that out of the 1,200 people that they test, 950 pass on the first attempt. So we know from past statistics, 82% of people pass the test on the first attempt. So I want to know, well, what's the probability for this testing centre that that will happen? Given that the national average, 82%, is what we're assuming it to be, what's the chance that 950 out of 1,200 people will pass at their first attempt? And we're going to make a kind of getting a little bit more into what statistics is all about and making an inference based on our probability we get. Alright, so the number of drivers who pass the first attempt is binomial. It's a classic binomial. N is 1200 and P is 0.82. So we're saying 82% pass on the first attempt. N times P, N times 1 minus P is greater than 5. Check. So we can use the normal approximation. We really don't want to be using the binomial formula hundreds and hundreds of times. So the mean is 984, the variance is 177.12. So X is approximately normal with those parameters. Remember, this here is the variance, not the standard deviation. When you go to use the formula, you need the square root of that in there. Okay, that's important. Okay, we want to know the chance that less than 950 people pass the test on the first attempt. Less than. The wording up here is really important. So our continuity correction, we go down to 949.5. Do the calculation, we get 0.0048. Okay, so let's talk about what that probability means. If the national average is 82% of people passing, for this place here, the average is way lower than that. It's actually not too much lower, but we've just worked out that given that the national average of 82% applies here, there's only a 0.0048 chance, or a 0.48%, or about 0.5% chance that you'll only have 950 people or below passing on the first attempt. That's a good evidence to suggest that the testing procedures at this particular centre are too tough. And I hope that makes sense. Only 0.5% chance that you'd have 950 or below at this testing centre. That's enough evidence for a statistician to say, well, looks like the testing procedures are too hard because the number of people that are passing on the first attempt is way lower than what it should be. So here's how I've written that up. So even though their percentage was 79%, not too much lower, the statistics that we've done here has shown that that's low enough. In fact, it's a very, very unlikely that you would get a value that low for a particular testing centre.